into the simple models. For example, I wanted to know the knee can, or the swing foot, or the foot can be extended exceeding some threshold or some convex hull with respect to the pelvis, for example. And also the center of pressure, maybe it needs actually to be bounded, or the angular momentum, if I have the angular momentum in there, the flywheel, for example, it can't just arbitrarily spin continuously, it needs to stop at some point. So all those things, I think, conceptually they make sense, they make in physical sense, so I think they need to be included as part of the simple model. But yes, they are, in some sense, still going to be suboptimal.
Okay. So in your slide 19, you had some nice video where you're walking on this broken cinder block, right? So suppose I had compliant and granular ground.
Right.
So think of styrofoam balls, lots of them. So how would your controller react to it, or what would you change?
So I think it would actually be better in this case than this case, because conceptually for the soft stuff, basically, or you can't really control center of pressure anymore. Like if you torque it, the ground is going to deform under your foot, which is roughly the same case here, because the rubbles, if they step on a kink like this, you can't really torque anything at all. But the good part for the sand, for example, is it sucks a lot of energy, so you won't have this high frequency vibration. In this case, sometimes it happens because in the controller it thinks it can torque this way, but if it actually torques this way, the foot and the rubber goes this way. So it could end up in an oscillatory case at the stance foot. But yeah, we haven't really done the soft sand thing yet. I think that would be interesting.
Okay, so one way to handle this is to turn off the ankle completely. Correct. So you have under actuation.
Correct.
So does your controller handle under actuation in any way? What do you think would the problems be?
I can easily turn it off. I just say you can't move the center of pressure in the.
It's still try to fight, right? To keep the center of pressure right in the middle.
But if I shrink, so I can shrink the center of pressure to be the region for the allowed center of pressure to be right somewhere under the foot, for example, to completely get rid of ankle torque. That's one way of forcing it to not use ankle torque at all.
That's not true. I mean, if you have a disturbance, the ankle will try to react to it to keep the center of pressure right in the center. So it's different from.
Oh, so you want to turn it completely into passive?
Yeah, so ankle torque equal to 0.
So I can, well, okay, that's another way of doing it.
What would fail in your control?
I haven't tried that, but I think or at least for my intuition, is if you walk fast enough and use foot placement, it should be all right. This is not the scenario you're talking about, but I think it's a similar problem we're facing. That is, can't use center of pressure anymore. It will be harder to get the robot start walking.
Sure.
If I can't use center of pressure from the double stance, but that's in detail.
Okay. So your value function is getting sent down your optimization, right?
Right.
So do you update your value function as it goes down at all?
I don't update it. I plan it every time I run the DEP thing, and then I keep it as is. So that's sort of what I want to achieve eventually in the future, but whether that's possible or not, it's not. It's up to the lower level guys to decide how feasible that is. But that's a representation of the intention of the high level thing.
Okay. So one last question. So a lot of your constraints are turned into optimization cost functions, and you have a whole bunch of weights.
Right.
So I see why you want to do it, to make the QP feasible always. But what do you lose?
So obviously I lose the last bit of precision. In some sense, my foot is always, it's not really, when you write down x dot equals j dot j q double dot equation, it's not really zero. You know, it's with some numerical things. And also, when I try to reach a target, I never actually reach a target. I reach a target, it goes down into a local minimum. That's, you know, the hand is a couple millimeters off from the target, but it somehow minimizing tweaks.
So how hard was it to tune the gains for this?
For getting precise motions, it's never really a big issue for us, because after we run it on a robot, it's never going to be precise anyway. So we're always relying on feedbacks, in this case provided by humans, to correct for the ineffective errors.
Oh, sorry, not the PD gains. So I mean the gains for your cost function.
The cost function stuff. It's by try and error. Basically, initially I say, I think the contact constraints, they need to be really high. I want to track center of mass because I think that's important. So I make those gains up. And then I run it on a robot. But if my center of mass gain is too high, the robot starts doing oscillations. And then I say, okay, I need to reduce it a little bit, or damp something more, or change the, penalize changing torques more, things like that. So it's a very, you know, tuning heavy thing. There's no rule of the thumb. Well, there's a rule of thumb. It's basically try to get the overall motion you want, or the overall behavior.
Okay, thanks.
All right, thanks.
Hartmut, you're up.
Yeah, I have two questions. The first one connecting to what Kaja was asking.
Yep.
So at some point you said that by doing model-based control you get away from hand-tuning all the joints controllers,
Right.
based on some policies. But right now you also mentioned that because you have all these cost functions and stuff, you also do a lot of hand-tuning. I just want to understand, it's like, how much less hand-tuning do you think you have to do as compared to a traditional policy-based approach?
So I think it's still a lot less, because essentially it boils down to, you know, 2 configuration files for all the things I do. And the amount of time I spend on tuning those gains is very, very little comparing to actually tuning things on the robot. Tuning the joint level controllers, tuning the gains for, you know, velocity gains or torque gains on the joints. The amount of time for that is much more than tuning the QP gains, for example. And the QP gains, they, in a sense, they don't change after, you know, it's after once I did it, I don't really have to tune in, even if the model is changed, the robot model is changed in most cases. So I still think it's a good thing to do these gains in some sense in the operational space. In a way, we are specifying gains in, you know, that's transformed by some combination of the Jacobian versus the mass matrix and, you know, all that stuff. So it does hide the actual details of the model. You're specifying gains in the idealized, you know, spring damper world of your hand, for example, or a foot. So I think that's still a gain.
And the second question, so you have worked on this for quite a while, you have collected a lot of knowledge. If you were to start from scratch, all the knowledge you have now, what would be the overarching theoretical problem that you would like to address?
So, let's see. I think the biggest flaw right now in this approach is you never know what's going to happen unless you actually run it. And that's something that, you know, is not very comfortable if you run it on the robot. So I would like to fix that. At least, you know, conceptually, you can generate a plan, but if somehow you can verify it before you actually run it, That would make me more comfortable.
How does this translate into a theoretical problem?
For example, if you have more constraints, or a simple model, or at least for the planners, have more expressive powers, they know more about the limitations of the system. That's one way of you do the plan, and then you can sort of verify it before you run it. At least for the important ones. For example, I think there's an interesting thing by Hongkai Dai and Russ Tedrick. Essentially what they do is they run a trajectory optimization for the kinematics, but they also do the centroidal dynamics in it. So they constrain at least the net ground reaction forces versus the joint accelerations. So if you don't consider internal torque limits, then the motion is going to be achievable in the end. So I think that's a very nice way of doing some planning, but not complete dynamics, which is still more reasonable than if you just fly center of mass through everything and see what happens. So this is relying a lot on approximations or conservative approximations you make about how far, for example, a foot can reach and how much center of mass can vary with respect to the foot. Those are all captured by, they have to be conservative linear constraints. But for example, if you actually consider full body kinematics, those can be all relaxed much better. It can probably give you a higher, more interesting behaviors. But also guarantee that the robot, at least, it's not going to rip itself out.
Okay.
Any questions from our audience?
Yes.
How accurate the placement in the fast walk?
Can you repeat the question?
So Julian's asking how accurate the foot placement is for the fast walking experiments. The answer is they're not very accurate either. About, I'd say around 5 centimeters if you are doing recovery steps. Sometimes more. Yes.
So your talk is about from the first step to motion control, right? So if you want to make some kind of real-time footstepping to the motion, so like based on slam to like continuous locomotion in some environment.
Right.
What do you need more? Like more degree of freedom or more accurate sensor?
So I think that's.
And again, if you can repeat the question.
So the question is, if I want to have a complete system that's planning the footstep and then generating the motion, in contrast to right now, what I'm doing is I would assume a footstep is planned by somebody else, and then I generate the motion part. So he's asking, what do I need, or what do I need more to accomplish that? So my answer to the question is, so obviously the sensing part is not fast enough right now, and that's the main motivation or the main reason for me to try to move away from generating footstep together with the actual controls, because I believe the control part still needs to happen really fast, and I don't want to have a dependency on the low sensing part. But on the other hand, so if you look at Pierre Weaver's stuff, he has a lot of basically walking without thinking, as he puts it. So he does the receding horizon part with the footsteps. So what he's doing is say, these are the blobs you can put down your foot, and for example, I want to go to the end of the hallway, but I don't tell the robot what's the footsteps. And by doing his receding horizon thing, he can try to lay down a set of footsteps, as well as generating the center of mass and the ZMP trajectories from that. So there are ways to do that. But I kind of think if you give the planner more time to come up with a plan, it will be a higher quality plan than having a laser point clouds and run your, some kind of NPC or trajectory optimizer together. I think that's just going to take way too long. I'm totally fine with if things happen, the robot has to stop somewhere and then do perception and planning again. Yes.
If the KVH is running at 1 kilohertz, let's say, and your joint control happens at 1 kilohertz, do you think that if you could run your QP for the inverse dynamics at 1 kilohertz, would you get better performance?
I don't think so, actually.
You got to repeat the question.
Right. The question is, if all the joint controllers run at kilohertz and somehow we get the QP stuff to run at 1 kilohertz as well, does it gain much performance? And my answer is, I don't think it actually does. There is a much difference between a 2 millisecond time step and a 1 millisecond time step at the QP level. A reason for that is, I don't know if Jerry's people are doing this, but at least for me, I'm actually penalizing the changes between time steps. I don't want the thing to do this kind of stuff. So in some way, I'm imposing a low-pass filter on the outputs of the QP thing. So I want to smooth that out. And in that case, I don't think going twice as fast is going to help in any case. The valve can go faster. The joint, I don't think it really matters.
So the valve has a bandwidth of roughly 200 hertz. And then the mechanical time constants are much lower. So it's not clear the system can, is going to respond to high frequency inputs.
Right.
Yes. Reverse level control is still running at 1 kilohertz. Even.
Yeah, the joint level stuff is still running. That's always running at 1 kilohertz.
So you're not updating your design terms, but the
Right.
device control.
It's just going to use the last settlements in games. Everyone has a question.
It was just with the sensing and control frequencies. Normally, it's a rule of thumb that you try to separate the estimation and control frequencies by an order of magnitude.
Right.
And it seems you didn't need to do this, or that you went to complications where estimation and control excite each other.
We actually run into a lot of problems with that, but only on. I shouldn't say only on. The only thing we paid attention to is center of mass dynamics. So there was, at a point, a lot of interaction between the state estimator and the controller, especially for the center of mass velocity. So a typical example or failure mode is there's some ripple in the center of mass state estimation, and that triggers my thing to wiggle, and then that in turn triggers more wiggling. So we had to spend a fair amount of time to speed that up. After we did so let me see how I should put it. At the end, for Ben X's thesis, we put IMUs on the lower body joint links, and those gives us faster estimation for the joint velocities, which in turn gives us faster center of mass velocity estimates. And that solved partially the interaction between the center of mass estimator and the controller problem. So the less delays we have from state estimation, obviously, the better.
Maybe then it makes sense to deliberately limit the update speed under control. So right now it seems you want to go faster and faster with your control. But if your sensing doesn't allow you to have higher and higher frequencies, you may run into fundamental limits. I don't look at it that way. I
I still think, I mean, it's like this, mechanically, there's a lot of, inherent damping in all the joints and stuff, so if you're not controlling crazy stuff, it's always going to be very stable in some sense. And the controlling crazy stuff part is coming from, for example, the delays or the phase lag between the state I'm trying to control and the state estimation of the real stuff and the real physical quantities. So I think I get hammered a lot by delays in the estimates rather than, and the gains I have on my control side, rather than how fast I run the control. But yeah, if I only control like once every 10 milliseconds, it's less likely I do this. It depends. If you're offset by the right amount, I think it will still do something like that.
Okay, the one thing I want you to do, Siyuan,
Yes.
is to press the off button exactly at the same time I press the off button here. So
Okay.
you're just going to whack the middle of the screen.
Yeah.
Ready?
Yeah.
1, 2,